the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. And we are in the throes of discussing the precise definition of a limit. And we've already gone through kind of an introduction to the precise definition. We've actually done the theory behind the precise definition of a limit and built that and talked about what that really truly is. And we've also proven at this point the limits for linear functions, finite limits for linear functions. Now, what we're going to focus on in this video, after you've already watched the previous ones, make sure that you understand what a limit is before watching this. What we're going to do here is expand upon our previous knowledge by doing something that's normally done prior to having the precise definition of a limit and all that fun stuff. So what we're talking about now in this video, you usually experience this before you learn the precise definition of a limit, but I find that this is a little bit easier to talk about after you learn about it. Plus, we actually developed this theory already when we were building the theory of the definition of a limit. So let's go ahead and just look at this example. Find some number, delta. And I never really mentioned this, but that delta right there is a lowercase delta. So that's lower delta. The uppercase delta, which I will erase here in a moment, the uppercase delta is the large triangle guy right there. So anyhow, find some number delta that's positive, such that as long as x is within that delta neighborhood of 2, then x cubed minus 8 is less than 10 to the negative third. Now let me give you the visual of this yet again, because we've kind of discussed this already, but it's super good to kind of see what this means. So we have a delta neighborhood. And remember, delta neighborhoods are all about x-axis neighborhoods or horizontal neighborhoods. And it's centered at 2. Notice I put an open hole at 2 because again, it's when we talk about neighborhoods, they're punctured open neighborhoods. And we know that the radius of the neighborhood is going to be that delta right there. So we have some neighborhood centered at 2 of radius delta. So this is 2 plus a delta, and this point over here is 2 minus a delta. It's an open interval, so we're not going to include those edges. You're probably tired of hearing that, but it's so good to constantly repeat it. And then what I'm going to do is just shade all the possible x values that are within that delta neighborhood. So all of these red x values here are x values that are super close to 2 within the delta neighborhood of 2. So that's what that shading represents, just to remind you. And we want to find the size of neighborhood, what's the radius of the neighborhood, so that when we look up and we see the function x cubed and we look at the value of 8, the distance between the function x cubed and 8, let me go ahead and just make a swoopy little curve here. Let's just pretend, because x cubed, you know, actually I'm going to zoom out here, or I already have, but x cubed, if I'm doing this appropriately, looks like the following. If this were the y-axis and this were the x-axis. So I'm going to pretend as though, and I don't need all this other stuff, so I'm going to pretend as though we have some swoopy little curve in here. Whee, just like that, okay? And we know, by the way, if you had plugged 2 into this, it would actually become 8. So we know as x approaches 2, x cubed approaches 8. We totally know that. But what we want to do is make an epsilon neighborhood about this height of 8, and let me go ahead and maybe use red here as well. So I'll go ahead and make this little height of 8 right here. Let's just pretend as though that's a height of 8. And they tell us that the distance between this function y equals x cubed and the height of 8, which is this line right here, that distance should be less than 10 to the negative third. Or in other words, we have an epsilon neighborhood, and I'm over exaggerating the size of this, I hope you know, but a symmetric neighborhood That looks somewhat symmetric, doesn't it? Of size 10 to the negative third, which is 0.001. So this is going to be 8.001, and this is 7.999. So we're hoping to find a neighborhood about 2 on the x-axis so that all of the x values in that neighborhood land on the curve and still within these horizontal bars here. And as you can see, the neighborhood that I've kind of just drawn out is not tight enough. So the delta there is just too large of a delta. And the reason why I say that is because if I grab this x value here and I map up to the corresponding y value on x cubed, you'll see that it lands outside. So again, that's our task. It's actually not too terrible of a task. Let's go ahead and see how we do this without using a graph. I just showed the graph so we could see this, but let's actually see how we do this mechanically. And this requires a bit of our prerequisite knowledge. In fact, time for a prerequisite. All right, so prerequisite knowledge. Just recall that the absolute value of something, people hate when I do this, but I'm doing it anyway. The absolute value of happy face is equal to, it splits into 2 possible cases. Well, if that happy face was already positive, or maybe I should say just non-negative, well then, there was no reason to have those absolute values on there. We could have easily just ripped those absolute values off. There was no need for them. So that's what we'll replace it with. Just happy face without the absolute values. If on the other hand, whatever was in those absolute values was negative, then the absolute values will force it to be positive by taking its opposite. And that's where we get the true definition of the absolute value. Sorry, I was kind of stunned at how horrible my happy face was there. Terrible, terrible. So what we're going to do is actually break this into those 2 cases. So this is how you do this algebraically. And I'm just going to let you know that often you cannot do this algebraically. But I just want to show you an example of how you would do this algebraically. And then we'll do another example of how you do this if somebody hands you an epsilon, because here they have actually handed us an epsilon here. How you go ahead and find out what the corresponding delta is based upon that specific epsilon, both mechanically and graphically. So I'm going to go ahead and maybe, yeah, I'll do this. So if x cubed minus 8 was already greater than or possibly equal to 0, if that was the case, then our absolute value of x cubed minus 8, by definition, we didn't need the absolute value. So perfect. And we want that to be less than 10 to the negative third, which is 0.001. Now what I'm going to do is go ahead and add 8 to both sides of that equation, or inequality, I should say. So that's 8 plus 0.001 or 8.001, and then take the cubed root of both sides. Now this obviously is going to go ahead and require us to use a calculator. So I'm going to pause for a moment and I get the following. X should be strictly less than 2.000083 on forever. Now that's a pretty specific. You can easily see that I'm paying close attention to the number of digits there. I also notice a pattern when I do that calculation. It is important that you do that. Now, this does not mean, because some people will look at this and say, oh man, that means X is super close to 2, which it is. How close? Within 0.000083 on forever. Yay. And they would say, that's the delta neighborhood. That must be the size of the delta neighborhood. And that's not necessarily true. While it is somewhat true, it's not necessarily true. But before we go ahead and delve into that, let me take care of the negative case. So let's take care of the other case. If x cubed minus 8 was less than 0, well then, we know that the absolute value of x cubed minus 8 is not going to return x cubed minus 8 because that's x cubed minus 8 is negative. We're just taking on that case right now. So the absolute value is not going to return a negative number. It's going to return the opposite of a negative number. And remember, what we know about the absolute value is that it's less than 10 to the negative third. So I'm going to go ahead and say this absolute value right here, which is equal to a negative x cubed minus 8, must be less than 10 to the negative third. Oops. There we go. Now what I'll do is I'll multiply both sides by a negative 1. Or you could distribute the negative. It doesn't really matter. The same thing, right? So I get that x cubed minus 8 is now greater than a negative 0.001. I'll add 8 to both sides. By the way, I should mention that your professor may not go through all of these steps. A lot of calculus professors, myself included at times, skip steps. I just say, well, you know that prereq and let's just move on. But I have no clue what your skill set is while you're watching this video. I have no idea. So I do take my time. Plus, honestly, this is a tough concept. So me doing the arithmetic and kind of showing my steps a little bit allows you time to think while I do stuff. So don't expect me to do this in a calculus video where I'm like, okay, now the arithmetic is like, that doesn't happen for much longer. Once we get out of epsilon delta proofs, then I go into high speed mode with my early computations. So anyway, if you grab a calculator, take the cube root of both sides, you will get the following, that x must therefore be greater than a 1.999916666, and then there's a 3. And I'm not sure if that 3 actually goes on forever, but I think it kind of does. So you could tell I'm keeping as many digits as I can because I just like to. That's just what I like to do. And now I'm going to zoom out, and you could see that for x cubed minus 8 to be less than 10 to the negative third, our requirements on x are that x be between 1.999916663 on forever likely, but that's what x has to be greater than. At the same time, it has to be less than 2.0000083 on forever. And the question is, remember, we're really trying to find out. I mean, now you can see right here, we have now found an interval, but the whole deal about delta neighborhoods is that they're symmetric. So you want to make sure this neighborhood that you're seeing right here is a symmetric neighborhood. So let's just take a look at these. I'm going to actually write them in terms of 2 plus and 2 minus. So if you look at the right hand side, that's actually the easier one. This is x is less than 2 plus 0.00, let's see, 4 zeros and an 8 and a 3 on forever. And on the right hand side, that is 2 minus something. And the best way to do that is just to grab a calculator and say 2 minus that. So I'm going to say, use that on my calculator, 2 minus answer. And man, that is a super small number. So this is going to be 2 minus 0.1234 and then 83336 8 ... It goes on forever. Okay. And actually, you know what? I'm very curious if the other one was not a repeatable 3. Now I'm somewhat concerned. Hold on a second. It was not. So let me zoom into here. That 3 was not a repeatable 3. It actually goes on. So I'm just going to put ... there. Do this ... because when I subtract 2 from that number, it actually gives me a scientific notation, and the scientific notation that I get comes out to the following: 0.00008332986135. Now look at those 2 wiggles. It's 2 plus a wiggle and 2 minus a wiggle, right? Notice those wiggle sizes are not the same. So I'm going to call this 2 minus delta sub 1. And this is 2 plus a delta sub 2. There's two completely different deltas, even though most people would probably say, listen, those are close enough to each other. They are actually definitely close to each other, I would agree. But I want to have this discussion because it's incredibly important that you notice something here. So let me bring us back to an animation, or sorry, an applet that I had earlier in a previous lecture. And if you take a look at what we have here, this is the epsilon delta applet that I've created on Desmos. And you see somebody's given us an epsilon neighborhood for a completely different function, about 2. So y equals 2. They gave us an epsilon neighborhood of 0.5. Let's say they tighten that up. Let's just tighten that up a little bit because it just seems like it should be. And our job was to find a tight enough delta neighborhood. Now, I'm going to zoom in. I want you to see something here as I zoom in. As I decrease the delta, notice on one side, pay attention to that left-hand side. Suddenly, right here, that left-hand side works. It becomes good enough. But notice the right-hand side, there's still y values that occur on our curve outside of that red epsilon band. And so while delta sub 1, which is this delta here from the midpoint all the way to where, actually I can click on it. Delta sub 1 is the distance between x equals 1 and x equals 0.7621, whatever that number is, okay? That's delta 1. That tells me, had I chosen that delta, that all of the x values that are less than x equals 1 would have y values along this curve inside the epsilon band. However, choosing a delta that size means that there are some y values that occur outside of our delta or epsilon band. And so we have to tighten this up even further until both delta 1 and delta 2 are small enough, basically so that we choose the smaller of those two deltas so that our x values lead into this epsilon neighborhood. So my point here is that when given the choice of two deltas, always take the smaller. In fact, when you have a delta, you can even go smaller if you want. It still works. So going back to the paper here, if you look at those two deltas, you have one that's this size. Just think of it, look at the 833, 368. That's probably the easiest way, because they both start with 4 zeros in front. And then you have the other delta over here. Between those two deltas, as small as those deltas are, one of them is smaller than the other, and so that is going to be your choice of delta. The smaller of the two deltas is going to be, let's see, 0.8333 versus 0.8332. This is the smaller of the two deltas, and so that will be our choice for delta here. Just like in the visualization we just saw, there were two choices for delta. We had to tighten it up to take the smallest of those two deltas. So let me zoom out. And it's just because the reason why you have two different deltas is because it's a curve. It's not increasing linearly. It's increasing, in this case, cubically. And so one side increases faster than the other. And so if they increase at different rates, your deltas will be different sizes on both sides. And so you have to choose the smaller of those two. And in this case, we will choose, and I'll actually write this, choose delta to equal the minimum of delta 1 or delta 2. This language I'm using on purpose because it gets used in a future lecture, so we might as well just get used to it right now. This just means the minimum of those two values. If you've done any type of computer programming, you know what that is. And so we know the smaller of those two values is going to be 0.0008332986135, and it's actually technically roughly that. Because I used a a calculator, and that's an approximated value, but that's good enough for me. Now, I don't know how many digits they want you to round this to, and I don't care. Mainly, I just care about the fact that I found the right delta. So this is how you would do this if you mechanically are finding a delta, so that as long as x is within that delta neighborhood of 2, then all the y values, or x cubes, are within this epsilon neighborhood of 8. So that's how you do that mechanically. Now let's talk about how you do it graphically, which is what we've been doing kind of all along. I'll move the page here. Use the graph of 6 times the sine of x, provided at Desmos, to find a number delta such that if the distance between x and pi over 3 is less than delta, and that's the positive distance, you see I kind of wrote that in there, then 6 times the absolute value of 6 times the sine of x, or I should say it this way, the distance between the function and the limit is less than 0.1. So let's go ahead and go over and take a look at that. Now, I've actually shown off to the left-hand side here the code, mainly because I don't always do that, but it's nice to kind of see what we're looking at. So we're looking at the function 6 sine of x. We're investigating what happens as x gets really close to pi over 3. And we want to find what is the size of the delta neighborhood required around pi over 3 so that the distance between our function 6 sine of x and the square root of 3 over 2, which is this line right here. This line is, I think that line is, no, that line is not actually. So I need to adjust my lecture slightly because that line should be at 3 root 3. So if I go back to here, this should not be root 3 over 2. If you're one of my students, you won't see this in your lecture notes because I'll have it fixed by the time you get there. But just letting you know, that should be 6 times that, or 3 root 3. Sorry about that. So we want the distance between our function, f of x, and our function basically evaluated at pi over 3, which is going to be the limit. We want that distance to be less than 0.01. So that's our epsilon neighborhood, 0.01. Wiggle by a tenth above, wiggle by a tenth below. And now we're back. So let's go ahead and make that wiggle. I think this is it. Yeah, make this wiggle a little bit less. Go down to a 0.1. So that's our wiggle size, a 0.1. And I'll zoom in here so you can see this. So it's nice to kind of see this. So this line right here is at a height of 3 root 3. That's what we're saying our y value should be approaching as the x values get close to pi over 3. And we're wiggling both up and down by a size of 0.1. And I actually don't think that's right. Okay, I did a quick fix on that code, so now it's actually working. All right, so we're looking at y equals 6 times the sine of x. And somebody's coming in, they're just changing the value of epsilon here. And remember what we were challenged with was an epsilon neighborhood around 3 root 3, which is what this horizontal red or orange dotted line is, of 0.1. That was our epsilon neighborhood. And we're tasked with finding the appropriate delta neighborhood so that all the x values in, let me zoom out and scroll down, all the x values in this delta interval around the value of pi over 3, that's what this value is, all the x values we want to lead into this horizontal epsilon neighborhood. I didn't shade it in this case, but you can imagine there's shading here in this horizontal epsilon bar. Now here's the problem. If you take a look at these values here, now remember, we're centering this vertical pipe here at pi over 3. So this is pi over 3 plus a wiggle, and this is pi over 3 minus a wiggle right here. And I'm going to write those on my separate piece of paper just so that I have those available to me, and then we'll move over there. But that we need to find out what the smaller of those two wiggles is. And it's not very obvious here what is the smaller of those two wiggles. And it's going to be incredibly approximated just because we're using Desmos, and Desmos is not super duper accurate when it comes to this. Well, actually, what you can do is off over here is you can compute what pi over 3 is. Oh, I already did. Pi over 3 is 1.0417 and so on and so forth, right? So if I go ahead and type in pi over 3 and I find the distance between that and the lower x value, so let's take a look at this one right here. It's 1.0148. Now, again, it's an approximation. You'll have to forgive me, that's not exact, but 1.0148. So that delta neighborhood is of size 0.03239, so on and so forth. Okay. The other one, remember to find the distance between 2 points, often you just take the absolute value, or you could take the larger value and subtract off the smaller value. The larger value here is the one that occurs right to the right side. Let me just zoom out so you can see this. Let me zoom out further so I can scroll faster. The larger x value is the one that occurs to the right. It's this guy right here. So it's 1.0816. So 1.0816. And we're going to subtract from that this middle x value, which is pi over 3. And that'll give us the distance between those 2 points. Now, if you look at those two deltas, it's the distance from the orange vertical line and the green vertical line here is the second delta, 0.0344. And the distance between the orange line and the leftmost green vertical line is the top one right here, 0.03293. And that actually is the smaller of those two values. So it's the smaller of the two deltas. And so therefore the appropriate delta would be roughly, I'm saying approximately equal to that number right there. So bringing it back to our handwritten page here, that's the delta that we're going to choose. So when you use technology to help you find the appropriate delta, let me just showcase a very fast way to do it. And by the way, what I've done is actually a fast way as well, but I'm going to show you another way. Now I'm back at Desmos here, and I've just created a blank graph, not that big of a deal. You can create any function you want. And so I'm going to create, let's do e to the x. Okay. And let's make it a little more wild than that. Let's go e to the x squared. Okay, that's a pretty interesting graph. A lot of people think it looks like a parabola. One thing I don't like on here is I don't like the grids. I like to remove them if I can. And let's pretend as though somebody makes a claim that the limit as x approaches 1 for this function is equal to 2.71828 and so on and so forth. And it actually is. So if I were to graph 1, and it's probably better if you don't call that y, call this f of x. That way we can do this quickly. If you look at 1 comma f at 1 and you label that, let's just say, there it is, right? So somebody says, I swear to you, that's the value of that limit as x approaches 1. And then somebody walks in and says, well, prove it. I'm going to give you an epsilon. I'm going to give you an epsilon neighborhood around the height of e, really is what that number is. That's that height right there is y equals e here, y equals e. So if they give you that challenge, let's say they give you an epsilon neighborhood of 0.01. So y equals e, this is how I would do it, plus 0.01 and y equals e minus a 0.01. Now you can't see them on there because it's such a small neighborhood, but there they are. That's my epsilon neighborhood. Forgive the underuse of colors there. Normally I'd use red or something like that. That's not a big, that's not a big deal. What is a big deal is that you're able to find out which of the two values, what is a smaller delta neighborhood. And so in this case, I'm going to go ahead and graph here x equals 1. And then what I'm going to allow myself to do is just move it so you can see something. Okay. Maybe I'll say x equals 1, and then the next one will be x equals 1 plus delta, and the other one will be x equals 1 minus delta, just so you can see this. And we don't have delta defined, so let me just say delta is 0, and we'll let delta go from 0 to, we don't actually need a super large delta here. So let's say it goes to 2 100ths, and we're going to step really small. Okay. So as I do this, zoom in. So all the mechanics are there. I have vertical lines at 1 plus and minus delta, so you can see my delta neighborhoods. And as you open up those bands, you see that delta right there is actually fine. It works. But what if we wanted the tightest delta? Well, it's very hard to see if you're doing this mechanically. But what I want you to notice is the best choices for delta are going to be, let me turn off these two vertical lines. Actually, I'll turn off that one too. Are going to occur when you look at the intersections of your curve with those horizontal bands. If you notice, the x value for where the horizontal upper band intersects the curve is 1 plus 0.0018. And where it intersects the curve on the lower line is a 1 minus actually a 0.18. So this, it's not actually a symmetric delta neighborhood, but as far as out to 4 digits, it is a symmetric delta neighborhood. So that is the way you would do it mechanically. You could trade this function out for any other function you want. I think we were just working with x cubed, right? So you could change that to an x cubed, and zoom out so I can actually see what I'm doing here. So there's my cubic function, and let's again pretend as though we're dealing with the limit at 1. So I'm going to go ahead and graph y equals 1, and we'll do 1 plus a wiggle and 1 minus a wiggle. And let's make the wiggle size 0.5. So the epsilon neighborhood we were handed is 0.05 is what I meant to say. So there's our epsilon neighborhood, and the green line is what our limit should be. All I'm going to do is click here, and here the intersection points. You can see one delta is at 1 plus 0.0164, and the other delta is at 1 minus, what is that, 0.017? So of those two, that's, you would just take 1 minus 0.983 to find out that's 0.017. So of those two, the smaller delta is actually 0.0164. It's just, all you do is take that number, subtract 1, that gives you the delta neighborhood, and you take the number here and subtract it from 1, and you'll get the size of that delta neighborhood. Take the smaller of those two numbers. I know that's a lot of me talking about that, but in reality, that's kind of how you're going to do it. And again, you could trade this out for any function you want. Okay, so that's how you do it on your own. And you'll see problems like that in most textbooks where they just say, hey, here's an epsilon neighborhood, find an appropriate delta, and you have two choices for a delta, always take the smaller. All right, that's it for kind of this mechanical part. And then in the next video, we're going to go back into proving limits, and it'll be for non-linear limits.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.